Yep.
Thank you. All right. Hey, everybody. Welcome to Deep Learning for Coders, Part 2. This is the final lesson of the series, lesson 25 on latent diffusion. Uh, the video begins with uh, a hint that there may be a Part 3 to this series. However, given kind of the length of time that's already passed since this series officially recorded, which was I think was in 2023. Not sure if we're actually ever going to see a part 3 there. So basically, we're not going to end up covering all of stable diffusion. There are a couple topics like clip embeddings, NLP that were, at least as of the end of this series, was going to be postponed to a part 3. And I talked about wanting to dive into ChatGPT 4. And really, I think that new series, How to Solve It with Code, probably does some of that. Although I'm guessing they don't carry the torch with this series per se. It's a little bit of a different um, theme there, right? Like low code, just using AI from a practical perspective, from what I can understand.
Right. And that's all like it's not publicly accessible, right?
It isn't yet. You figure like eventually it will. I've been checking out to see if they're gonna post stuff on YouTube, but Jeremy's channel tends to be good at presenting content. Just haven't seen anything lately.
Okay.
All right, so this video covered, I think, 4 different notebooks. We may go through some of them a little bit, but at this point, we're not going over a lot of new topics. But the first notebook was pretty interesting. It's just more of a different application from what we've seen so far. So instead of dealing with images, we're dealing with sound. Um, it kind of reminded me of uh, part 1 of the series, where I think they kind of alluded to the fact that you can represent like a time series, right, with an image. And so here we're dealing with bird calls. John will walk through a notebook um, in Google Colab. And basically, we're trying to generate our own bird calls from the original samples. And long story short, what we end up doing is creating pictures from these audio samples. Ron or Torn, I don't know if you actually ran this in Google Colab. I had some issues with that, some versioning issues, and was trying to upgrade the default pip, but I just for about like 5 minutes of not getting where I wanted to be, I kind of gave up. So I didn't formally run this notebook, but um, I get the gist of what was going on. Did you
I
guys?
did, but I can't remember. There
Yeah.
was some issue, and I forget how I solved it.
Yeah.
It wasn't
Here's one of the errors I had. No module name diffusers pipeline
right, right.
audio.
Yeah,
Yeah.
the problem was the Mel thing's been moved.
Okay.
That was
Gotcha.
that been moved somewhere else. Let me see if I can find my note so we can get it in the record. Um,
Yeah, that would be helpful, I guess, for other folks watching this, and maybe you have a solution, I might try it later.
yeah, it's just like one change. I think that's the only change you needed to do.
I didn't. Yeah. But I really like this example because like
Yeah,
that's
yeah, for sure. Well, I'm
okay.
gonna I'm gonna keep going on in this, and if you have a
Yeah, you just have to change it to from diffusers, import Mel. Not all that. You don't need all that pipeline, blah, blah, blah. Just take out everything. Just say from diffusers, import Mel, and that's it.
um, sorry, I got my dog barking in the background. Um, but Ron, if you wouldn't mind posting that in the chat, that
Yeah,
would
it's
be
just change that
helpful.
line so it just says from diffusers, import Mel instead of all this other
Oh, I
stuff.
see. So I can maybe do this live.
Yeah.
Um, See if that works. Whoops.
You cut way too much. Not way too much, but slightly too much. Yeah, I hate that's something that yeah. There you go.
Come on, no whammies.
Thinking about it.
Actually, this does take a while to run from what I recall. Oh,
That was it saying.
that's interesting because I didn't get that message yesterday
What is
about the.
minimum mini? Does that you type in something?
I think it is mini AI though. Oh well.
I
I'll
didn't see. I didn't get that error.
yeah, I didn't either yesterday, so that's
Maybe you type. Maybe you somehow copy pasted something and just actually double up the mini part because it's just mini AI in the course.
it is in the course, but I thought they had a
Okay.
mini AI, specific to
Oh,
this.
I see. I see. Shrinking it. Stuff. Yeah, it could be out on I'm on the website to see where it is.
Okay. Well, let's just move on here. So, one of the things that was brought up here is, working with audio data, is a little bit complex here. You're dealing, in this case, 32,000 samples per second, right? So you have essentially a pretty big data set with just a couple seconds of audio. A lot of background noise that you can get with audio samples, some really high frequency components, and of course you have temporal dependencies that you have to deal with as well. And so the solution that they come up with, we're converting this audio to an image is something called a spectrogram, which is pretty cool. It conveys frequencies on the y-axis, x-axis is time, and then there's some color coding to show intensity, and we can look at that real quick. Yes. So this would be one of this different frequencies on the y, and colors would indicate intensity, or most likely like decibels or something.
Incidentally, you're right. It is mini AI, so I don't know what's going on there.
Yeah, yeah. I guess that's the one they would have had saved out on
So the pip
PyPy or
install didn't
something.
work. I don't know. It's weird.
Yeah, I'll just have to play around with that later because
Yeah.
I also did not get that error.
Sorry to interrupt this.
No, all good. And so we have a spectrogram. Jono did this cool demonstration where he had one running live, and like he was playing like a harmonica, and you could actually see the different
Yeah.
frequencies lighting up. I thought that was cool, or like whistling at a different frequency, like starting low and then going up high, and you could actually see those frequencies lighting up. So yeah, really, really interesting demonstration there. Because we're interested in reproducing sounds that are realistic to us, right? To human ears. They use something called a MEL spectrogram. So really that just focuses on the frequencies that we can hear. We don't care about like if bats can hear, think it's a
Right.
realistic reproduction or not for this kind of example. And then the other thing is that the frequencies are log transformed. And they made a point to say that this is a lossy compression, right? It's because you are losing information by applying this spectrogram. And then one last piece, there's when you're dealing with sound, you have phasing issues. And under the hood, with what they're applying here, there's something called a Griffin-Lin algorithm that iteratively tries to solve for that particular issue. I guess you could also use a deep learning approach, but this Griffin-Lin thing is pretty standard for audio data. Despite the fact that I couldn't run this notebook in full, I do think we can just play a couple of the samples. Did you hear that?
No.
Ah, that stinks.
What I've heard of, I've listened to them.
I
Yeah.
think when you share, you have to say you want to share your computer audio. But that's
Yeah,
okay.
Oh, that's a thing.
Let me see
Yeah,
if I
there's
can
like a little checkbox at the bottom. It opens all the
share
screens.
sound.
Yeah.
Good call. Thank you.
Wow, I never noticed that.
Yeah. Okay. Go back there.
Oh, yeah, now we hear it.
So it doesn't sound great, but the original audio also wasn't amazing. So I think that it's a pretty faithful reproduction of what we're doing.
Yeah,
Yeah,
reproduces the noise and everything because that's what's in the images, right?
pretty crazy. Could
Yeah.
make a lot of like sci-fi animals, I guess.
Oh yeah.
Sounds.
By the way, if you want to see like what state of the art, and I mean, you probably have seen this from posted in here called Suno. It's like one of the state of the art music generators you can play with. You can like type in like, hey, make me a song about Bayesian statistics and whatever, like make up an entire song with lyrics and leads and bridges and everything. It's bizarre.
Yeah. If you have a link for that, that would be
I
cool.
did. I put it in the chat.
Uh,
I point to
yeah,
it like you can see it. It's
Suno.
right there.
I did play around with Refusion, which does the same thing. And actually, let me
Okay.
go
Does it
back
do? I
again.
didn't actually. For some reason I didn't play around with that. I assumed that one just did like the music part, but not the lyrics and singing.
Oh, yeah, this one actually produces lyrics
Oh,
and
same thing. Okay, I didn't
yeah,
realize that.
yeah. And so my understanding is that Refusion uses a spectrogram as well and a VAE under the hood, which is why they kind of pivoted to this after the bird call sample. And I
How's
did a
this one sound?
bunch of songs. I'm a music nerd,
Yeah, me
and
too.
yeah, and I play instrument. I could tell you, obviously, you have guitars in the background. You play. I play multiple instruments, but um, I couldn't really get this thing to produce anything except for like just glossy,
Uh,
disgusting sounding stuff. But let me play a couple examples for you, and it shows you what my prompt was. It said like indie rock, whisper vocals, lo-fi guitar, slow haunting, big drums, trip hop. That one's bad. Let me do something else. Oh, here we go. Like grunge, raw bedroom recording, dynamic, loud, quiet, contrast, gritty vocals. Um,
that
didn't
was your
like how this.
prompt?
That's my prompt. Fast forward.
Sounds lo-fi-ish. Raw bedroom recording.
Well,
Yeah.
it only sounds lo-fi, I think, because of the audio setup with my sharing, because I think it's in mono. But on my computer, it actually sounds like high fidelity, and it reminds me of like Filter from like the mid '90s or something like that.
Yeah, exactly. But you should have put in there like what you want the song to be about too. You can do that, and all that lyrics will be
That's
tailored to
true.
that.
I didn't really focus on the
Yeah.
lyrics, but yeah, they do print
Oh,
out.
wow. Do you know how they
Yeah, can you
get
fast forward? Oh,
like
sorry.
different lengths of time on the output?
I think but what I did a little bit of reading, as far as I can tell, they use like something, they use a transform out, like probably chat, maybe they even use OpenAI's ChatGPT thing to generate the lyrics first from what you said. And then they use the lyrics somehow to structure the song. Like they match up the lyrics and then to the rhythm, maybe in the spectrogram or something. I'm not sure. But then, I mean, they actually have singing. It's amazing.
Yes.
So
Yeah. I mean, it
I
sounds,
don't know how that
again,
works at all.
I'm not doing it justice by sharing it here, but yeah, I mean, it sounds realistic. I mean, these sound like, professional singers. It's just that the songs themselves were pretty boring. Now, again, like I didn't really do a super detailed prompt for any of these, which is kind of with any sort of like large, like if you're dealing with LLMs, right, you need to be extremely detailed to get good results and iterate. But yeah,
I mean, I didn't play with this when I played with Suno, and I was really impressed. Like I said, give me an 80s hairband style heavy metal song about
okay,
my friends playing D&D with me, and it comes up, it's like it sounds just like you'd expect, even has like a little
that's cool.
bridge section where it goes down, like down tempo a little bit, it cuts back strong. Like, wow.
One interesting change to this website since the video was recorded is it seems like you cannot say do something in the style of like Scott Joplin, which was one of the examples they
Right.
had.
Yeah, you
It
can't do
says
that on any of them
you
now.
can't do
Yeah.
that anymore. I'm sure they've got threatened with lawsuits or something like
Yeah.
that, or they're
Well,
worried
they are
about
getting
it.
sued. Like Suno, I know is getting sued because they claim that they were you people claim they were music, just like the image thing. The people they did, I'm sure, use lots and lots of 80s hairband, for example,
Yeah,
the training data, right?
right. Yeah, so you're not gonna can't do Bob Dylan or Kurt Cobain or whatever. It
Yeah.
doesn't work. You have to just give more of a generic prompt in terms of like genre.
Interesting though. That's it's really fascinating. It's kind of both fascinating and also kind of disheartening. It's like, well, why even bother with my guitar anymore?
Yeah. Well, I think the next kind of evolution of this, right, is like you already have a song that's
Right.
like partially complete, right? And it can kind of take it from there and add parts.
Oh, can you upload songs to this thing?
Uh
You can to Suno.
no,
I don't know what it does.
I
It says
I don't think
upload
so, but
sound,
I
but
have to imagine that exists or will exist soon.
Hmm.
it says
Um,
upload audio is a button on the Suno one. But that might be one of the pay
okay.
levels because there's different levels you can
Yeah.
have to pay to do stuff. I haven't experimented that
What
far, but
this does have is it has a remix button. So like if
oh,
you kind of liked something, you can kind of redo it, but still in the same style, right?
uh,
So it's just kind of
that's cool.
recalibrating the randomness,
Hmm.
right, to something a little different there.
I thought it would be cool if you could actually just mix it. Like, well, I don't want the vocals. I just want the music part so I can sing my own on
Oh,
top
you
of
can
it.
do that. You can
Oh,
do
you
that.
can.
Yes. See, instrumental?
Oh,
Yes or
okay.
no?
Very cool.
Nice.
Yes, but I certainly would not buy any of these songs that I generated. They were so awful. Very professional, but also awful.
Well, I don't know if I should send you this link or not. Like, I don't want the whole world to hear this thing.
Just put it in the private chat on Slack.
Yeah.
Yeah, there we go. Okay, so that's basically it for that audio example. This was just using kind of a similar diffusion model to what we've looked at before, so I'm not really going to go into those details. We then move into autoencoders and VAEs, notebook 29, and we start with the fashion MNIST image data set once again. And Jeremy kind of goes through like, okay, this is how a basic autoencoder works. And I'll show you the notebook in just a second. But what we're doing is we're starting with 768 length vector, right? Because we flattened out an image, and then we're compressing it to a 200 space, and then trying to decode it back. And so we scroll to the top of this, and we can kind of look at that, what those results look like here. Yeah, so pretty basic linear layer kind of goes in with this. Input, sorry, 784, 400 hidden units, and then at 200 output. And training was a little funky there.
Yeah.
Didn't notice that until now.
Well, that wasn't training. That was that learning rate finder, wasn't it?
Oh, is that what that was?
I assume.
Yeah,
Yeah.
good call out. Yeah, the learning actually looks really smooth. So here are the original images from the first 9 here. And when we decode it back, you definitely still see clothes here, but things are kind of blurry. Okay. And it makes sense, of course, because these are compressed. It's not going to produce like high resolution images. And so then the other thing they talk about is, these standard autoencoders are not really good for generation. They're good for compression. But it's not going to do a good job if you're starting with like random noise. It doesn't really decode back to something that looks similar to your original training data. And we can see some examples of that. Right, because we're dealing with clothing, and for the most part, I mean, yeah, some of these you can kind of make out an outline of some clothes, but it's very ambiguous in most of these cases, what we're doing here. You know, what these are supposed to represent. All right, so then we move on to variational autoencoders. And these do quite a bit better of a job, right, of generating images here. We're creating a more structured latent space for doing this. They talk about this as being a good natural segue from the spectrogram diffusion that we just walked through. And again, that Refusion website apparently, I think, uses both spectrograms and VAEs under the hood. And we end up starting with a similar encoder. It's actually the same same encoder that we used in the autoencoder, but we're changing the final layer where we have 2 outputs, not 1. So a mu and LV is log variance. And this is pretty interesting here. The loss function that we're using is a combination of 2 things. One, we're using binary cross entropy, which is really just used to measure whether or not our generated images look realistic vis-a-vis the target image. But then we're also employing K-out divergence loss. And this, K-out divergence, I think, pops up kind of all over the place in machine learning and statistics. But here, what we're really trying to do is just say, does this look like a standard normal distribution? And again, we're kind of generating vectors of means and variances as output, right? In that, and initially this is all going to be random stuff. And so by employing this KLD loss, that's going to help us get to our end goal of producing in the latent space something that's looks like a standard unit normal. And so our total loss function, what we're doing is we're just adding those 2 losses together. We're not like really weighting one versus the other any differently.
Yeah, I mean, you wouldn't. I mean, so this kind of misleading in how he does this, right? I mean, I think people present this all the time this way. It's like, oh, we're going to combine the binary cross entropy, and then we'll just add this KLD loss. He does say, like, don't worry about the details or whatever.
Right. Sure.
But if you're interested in the details, you should look into it, because it turns out all you really have is one loss. It's KLD loss between the posterior. It's a Bayesian question, right? It's the posterior distribution of those parameters, and we have this Gaussian approximation, and the standard deviation, the unit normal there is actually the prior. And so if you work through all the math, the KL divergence between the approximate posterior, which is the normals and the latents, versus the true posterior, right? You work through all the math, the KLD divergence, you get both those terms out of the KLD divergence. So the first one is the KLD divergence between the posterior and the prior, which is the normal. The second one is what's left over. It basically turns into the negative log likelihood for the data.
I was going to say that's just the negative log likelihood of the standard normal.
Yeah.
Yeah, he spent a long time, like, I don't think he did a good job talking about
this part,
through that. I was like, you are making this so complicated.
Yeah. He's trying to avoid
You did much better job, Aaron. Much better.
I liked how he described the KLD loss, though, as like a regularization term. I mean, that kind of resonated with me, like a guy, who uses like ridge regression and lasso quite a bit, right, in my day-to-day.
I mean, in fact, there's nothing wrong. There's nothing can stop you from, like, and that's the mathematics. Nothing can stop you from, like, well, let's try scaling these differently and see what happens. Nothing can stop you from doing that. Maybe you might get better because it's all empirical at that point.
Yeah.
All right. You are right, though. He spent a lot of time on this. Yeah, I took quite a few notes on it. I don't know if I really missed anything there or not. The key point with the VAE is we're mapping a distribution in the latent space and not a point, right? I think that's kind of the key of
Yeah.
why this actually works better for generation
Yeah.
compared to the the autoencoders. Yeah, and the idea there is if you map 2 points that are similar in latent space, when you decode it, those images should look similar to each other, right? That's the kind of the main point. And then Jeremy kind of asked Bing a question about problems
Oh
with
yeah,
high.
that's right.
Like I wouldn't do Bing anymore, right? I go straight to like Gemini or ChatGPT. But yeah, problems with high and low variance. I mean, this obviously makes sense. Like with if you have too low variance, you're not going to really have expressive output. Everything's going to look the same. If the variance is too high, you're going to get nonsensical outputs. It's way too noisy. Okay. In the notebook, Jeremy, we can look at this if you want. He produces the separate metrics, I believe, in callbacks for the KLD component and then the BCE, the binary cross entropy. Just likes looking at those for whatever reason. And he points out that the BCE loss for the VAE is higher than the autoencoder, but that makes sense because we have a different loss function here, right? We're trying to balance the two losses that we're combining into one. Let's see. He talks about how the VAE itself is not, when you try to just decompress your training examples, it's actually worse than the autoencoder, which makes sense. And that's what I'm showing here. These are the same 9 images that we looked at before. With the straight up autoencoder, we actually at least saw, we didn't get the letters, the Lee word here, but there was like some white stuff showing, and here we're not. So it's a little bit rougher. But again, that's not what this thing is intended to do. It is, in comparison to the autoencoder, like we're producing images that are, while still blurry, look like clothes, right? And that's kind of what we intended to do here. So we've successfully generated new clothing that was not part of our original data. Okay. Trying to remember here. The next item on the list was dealing with bigger images. This is notebook 30. And I think they were 256 by 256. And this is the Elson data set. And specifically the Elson bedroom data set. And you can look at a couple of scroll to the top here. Got a couple of those images here. So they're, pretty detailed. And all bedroom themed, as we would expect. Jeremy likes to go through little Python tips, right, for managing downloading and dealing with data. I think he does that in this notebook as well. But we're starting with a pre-trained VAE from diffusers. It's this autoencoder KL from pre-trained. And what we do is we end up running that through the encoder, and we end up with in a single batch. And I guess the batch size was 16, 48 times smaller than the original images. So a lot easier to work with in terms of compute time. You're going to be saving a lot when you're working in that smaller dimensional space. So we went from 16 images in a batch, and your normal 3 channels for red, green, and blue, 256 by 256, Now we're down to still 16 examples, but 4 channels and 32 by 32. And I think he actually shows you what this latent space looks like. Of course, it's 4 channels, so he's just showing the first 3 channels, right? Because we can only see so much. The four-dimensional space is harder to represent, but you can still kind of make out like what's going on here. Right? These still look like bedroom scenes. You can see beds in most of these images here.
And just to be clear, this is using a pre-trained model, not that he just downloaded, right? Not something,
This is pre-trained models. We have not tuned it at all.
right?
Yeah, this is just the latent space. And then when we try to decode those same images originally from that latent space back to the space we're interested in, this is what we get. And it looks pretty good out of the box. One thing they talk about is these things tend to struggle. I'm trying to zoom in, struggle with words, maybe even numbers. And you can kind of see it here, like the first, second, third on this this chest of drawers, right? Like you can see the first seems like it reproduced okay, but the second, the ND on the second and the third just didn't really come back as you would expect. And another call out in the video was just that, I guess, faces don't always, and it's hard to see here because these are already just these smaller images, but they, I guess, you don't get a lot of the detail that you would expect with faces. Okay, yeah, and
Sorry, I
then
just quick observation. I think
sure.
that means that it is like already doing some kinds of hallucination, right? So it wants to create detailed lettering on the dresser because they're there, but it doesn't have the information or the ability to put them the way they were,
That's right. And I guess I haven't really looked into this much, and a lot of the examples that we've dealt with so far didn't have like letters or numbers in there, right? Like do you need to do something special for these models, right? So they know to reproduce something that actually is readable to us, right? And not just like, here's a shape that kind of looks like a number or a letter.
I
Maybe
know the
it's like
dollies.
that
Go ahead.
song thing that you were saying, generating the text first and then the
Yeah,
music.
yeah,
I know
that's a good
Dolly's
point.
gotten better at it over time, but still not perfect. Like sometimes I get the letters out of order, but at least it gets letters that look like letters.
All right, let me see if I missed anything here. They talked about this pre-trained VAE using perceptual loss, but also adversarial loss, which is generally how GANs are trained. You guys probably have stronger background in that than I do. But there's this iterative approach, right, where you're kind of generating these images, and then it gets sent to the discriminator, and the discriminator returns an output. And there are different ways, I guess, these discriminators work, but a lot of times it will just be like, well, you send it like a fake image and a real image, right? And you try to trick the discriminator to give it a high probability that it's a real image when in fact you sent it a fake image, right? So there's this iterative process where you could train a generator on its own, right? With a separate loss function that gets fed to a discriminator. And it could get to this point where the discriminator is just very good. And so then you might want to, go back to the generator. You're right, that gets better over time, and it gets sent back to the discriminator, just kind of a ping pong back and forth of these two models, so that you end up with a much better images overall. I guess what the discriminator does in general is it helps to reduce the blur that we saw in some of our outputs so far, right? Sharper, clear, realistic images.
Yeah, one of the
Um,
students, one of the I don't know if they're students, but one of the other people that he has in his chat, who are they? Are they postdocs or something? Anyway, they were making that point that, hey, if it's blurry, it's a dead giveaway. So, at least do something sharp, even if it's wrong.
Yeah, no, for sure. Yeah, and I think actually later in the video Jeremy just met these guys on Discord. So it's like
Oh,
like, hey, like you could be on these videos too if you just reach out and participate on Discord.
oh, wow, I didn't know that. I assume they're like all in the same university or something,
But
or
the
whatever.
younger guy in the video, I think he's kind of he was a childhood prodigy. I think
Oh,
early on in the videos, like he was on like Letterman or something when he was 8, because he was
wow.
like in college already or something. I think it was that
Oh my
guy.
God.
How did I miss
I
all
don't
that?
think Jeremy is an academic.
Oh, he's not.
I don't think so, no.
I think you're right. Now you say that, it does ring true. I guess I just assumed.
Yeah, there was a reference to a fast AI lesson from 2019. So I guess the whole idea with the discriminator and generator, kind of that iterative process, they highlight that in an earlier version of Fast AI if you want to check that out. All right, and this part I pretty much glossed over, but he talks about dealing with these efficiently saving the encoded latents using this thing from NumPy, this memmap. Um, Ron, or Torin, have you ever used this before? I was unfamiliar with it.
No, I've never even heard of it.
No.
I use NumPy all the time. Never. I tend to use like Feather and Parquet files more than anything else these days, but that's kind of a different application than what these are for.
Yeah, and again, this was just kind of like a niche detail.
Yeah.
I think more of a workflow thing more than anything else, as opposed to modeling, right? But he mentioned something about like, okay, normally like memory that would be in RAM is being moved to the hard drive. Um, there's something special under the hood that does this sort of transfer. Um, so it's just kind of an FYI if you want to explore. That's one way to do it. Okay. Let's see. I think we're still in this notebook. Um, and basically we want to get to the point where we're generating new images. We do the kind of the noisify process that we have been doing for weeks now, and then decoding. Um, Jeremy actually trained, I guess, for a few hours to do 25 epochs. The other gentleman trained for 15 hours on a single GPU for 100 epochs. And I think we at least see Jeremy's results and Tanish, if I'm pronouncing that right. His
Yeah, I think
results
that's
were
right.
only marginally better
I couldn't
than
see that they're better at all, but on the
yeah.
video.
So let's see. Yeah, here's the noisify process that we're used to, right? You start with random noise and then um I can't remember. Is this the latent space we're looking at there?
Yeah. No, what is that?
Oh, we're decoding the random noise. So
Right.
this is
The
just
noisified
untrained.
images, yeah.
Yep, yep, yep.
Just to
Okay.
see what they look like.
Yeah, and so then we train, and let me zoom back out a little bit. These
Some look good, some
the
look
one on the
terrible.
top left looks kind of like a murder scene.
I don't know what went wrong there.
It does. Oh my
Yeah, it
gosh.
looks like blood on sheets. I don't know. It's a little scary. But yeah, I mean, you see some of these are better than others. Yes, you can certainly make out.
What is going on there? That guy's got a lot of drapes or something.
Yes,
Yeah,
yeah,
it's like curtains and wallpaper
Roman
meshing or
shades or
something.
something like that. And
Yeah.
bottom right just looks like a really messy, just trash all over
Space.
the bedspread. So yeah, not great. And I think the extra, hours that Tanish invested didn't really do much for him. It
But you have
kind
to
of
think
looked
like
like,
if you just were the one that thought of this idea, well, you know what I'm going to do? Doing this stable diffusion takes so long on the image space. I want to use a VAE and do the stable diffusion on the latent space, see what happens. And you see this, you'd be like jumping up and down, like, whoa, right? The first time. They're pretty
yeah,
good from that perspective.
yeah, no, for sure. Uh, yeah, and they of course had some just comments, like, how do we make this better? And I guess their next step would be like, well, let's train this on a larger data set, right? Well, that never hurts, right? When you have more data. So like this was a subset of the LSUN data set. Like let's throw the whole kitchen sink at it and maybe we get better results. All right, and so the final section referred to notebook 31, and it wasn't really fully fleshed out. It was more of like a concept, like here's one thing you might want to try. And as of the time of like when this video was recorded, I don't think people were really doing this. I don't know if it's commonplace today or not, but um, so he starts with the ImageNet data set. Um, and he's like, well, wouldn't it be cool to train a classifier on the ImageNet data set, but working in latent space, right? So you start with I think you just use the diffusers kind of model kind of out of the box, right? To encode it into a latent space. And then you kind of train the classifier model on that. And that could be an interesting model once you've trained that, right? For doing some more sophisticated diffusion approaches. And they don't really take it much further than that. They just said, well, like here's one thing you might want to try, and then once you do it, maybe you can have you know
Yeah,
that's a means for doing further research once you
right.
accomplish that task.
If
But the
you're
one,
interested in it.
yeah, the one thing just from this notebook thought was interesting. Yeah, so here's the latent space. We've seen that before, decoded. Looks pretty good out of the box. But and he applies a bunch of transforms to this like you would expect. Um,
Augmentation, yeah.
yeah, and so I guess this looks funky because we're decoding it before training, but like we've done things like the random noise or random erase
Well,
and
remember he's trying to train a classifier here. So
yes.
he wants to give it things that have been messed up a little bit to make the classifier
Y-
uh
Yeah. So
work
he's
harder.
already kind of done, whoops, he's already done that and in the latent space, and now we're
Right.
kind of
And
decoding it back. So this
just to see, yeah.
we wouldn't expect this to look great because
Right.
we haven't trained anything yet. Um, the point I just wanted to call out here is the results are pretty good as just as a standalone classifier in latent space. It does a pretty good job at classifying. So like just looking at accuracy, it doesn't start off very very high, but you have to remember this is like 1,000 different buckets, right?
Yeah.
So
Yeah.
even like a 23% accuracy starting point is not awful, and he gets up to you know
66%.
yeah 66% on the evaluation data set. And compared, they were calling out like AlexNet, which was probably about what 10 years or something old now, but like this would have been state of the art
Yeah.
10 years ago. So this already is not a bad classifier, just working in the latent space.
Yeah. I don't know why he was surprised though, because all the information we already could say you can see all the information is still there in the latent space. Because we transform it back, it looks like the image. So I don't think this classifier doesn't care. If you
Yeah,
mess it up a lot by encoding in a weird way, it'll
yeah,
just decode
I
if it
agree
had
with
to.
you. And actually, you would think that might help, right? Because you're
Yeah, it might help if
getting rid of
anything.
some of the noise. You're focusing on the most important aspects in lower dimensional space.
Yeah.
Yeah, you would think that would
I'm
work.
basically just attaching a front end to the classifier that does a bunch of the work already for you. And now you can go on and continue on doing the work. But yeah, so I found a good representation for the image now classified. So yeah. But his goal of doing that was if he trains the classifier to do that, then you can use it for the half of the VAE, right? The encoder half. The
Yeah,
VAE.
yeah. So that
Mhm.
was the next step. They just,
Or not the
took
VAE for the, not the VA for the
for
for the
diffusion,
diffusion. Yeah,
for
they call
diffusion
the
model.
upstream. Yeah, the upstream part. Interesting. Yeah, good.
Yeah,
Nice,
so
nice job there.
that's, yeah, so that's basically it. And they just, yeah, give you some ideas
What
for
to
moving
do?
this
Yeah.
forward. And hey, if you've made it the whole way through Fast AI, what do you do now? Like read papers as they come out. They encourage you to join the Fast AI Discord because there's, I guess, a pretty active community there, and just collaborate with others.
I don't know. It doesn't seem that active now, but maybe it was at one point.
Oh, is that
I
right? Like
put,
I haven't been on there.
Yeah.
it might get more active with the new course.
Doesn't seem like the course is directly related to it. But I don't know.
I posted in chat. I think Jeremy interviewed Tanish. So yeah, it says he graduated high school when he was 10 years old.
Oh, I didn't know there was a
Um,
podcast. That's cool. I also posted Jeremy Howard's like Wikipedia page because I don't know why I just assumed he was an academic this whole time and I never
He
looked him
kind
up.
of acts like an
Well,
academic.
he's an educator, I guess.
Yeah.
But I didn't know he
Right.
was a fountain. He kind of made his bones with Fastmail, which I never put those two together, Fastmail and Fast AI. But Fastmail is what my old company used to use back in,
Yeah.
20 years ago or 25 years ago. That's so
It-
funny.
he's been involved with so much stuff. Like in one of the earlier videos, like he in a consulting role was selling like pricing optimization and insurance, and that's like kind of what I
Ah,
do. But this was probably like late 90s, early 2000s,
but did you look
using
on
machine
there?
learning.
Yeah, it's amazing. But look on there, he said first became involved with Kaggle after becoming the globally top ranked participant in data science competition in both 2010 and 2011, involving tourism forecasting. He then became president and chief scientist at Kaggle. So I guess winning those competitions can get you somewhere.
Yeah.
That's pretty
Yeah,
amazing.
yeah, for sure.
It was
Yeah,
only
and
founded in 2010, so wow.
he has that fast HTML thing now. I think we talked about that a little bit. I
Yeah.
don't know much about it, but right, just the idea of creating web pages more quickly with Python. Um, and he also has this answer.ai. I don't know if you've been to that website, but it looks like fast AI in terms of its layout. So use a similar web template. And that seems
Oh
to be
yeah.
more active than the fast AI website in terms of like blog posts. And it's some of the same characters, like Jono is posting on that thing. And I guess they're producing end user products. They're describing that. So I don't know if that's all, assuming it's all open source and they're just, doing their own research and posting their findings on there.
Hmm.
But yeah. That's all I have. I'm gonna hit end in the chat.